Okay, so yesterday I did some random videos with my phone. I'm going to do the same thing today. A little further along, so I made some of these. I made some holders for my router right here, spindle. What I'm using for spindle, and I milled them over in the little pedal mill in the back there. So I still got a couple operations left on those to make that happen. And there's actually another set of those right here. So there's two sets of those. Actually, here's the drawing. So if you can see that, I'll zoom in a little bit. I'm still missing some detail. First of all, I didn't have the router in there. But you can see the two brackets that I made out of 10 series aluminum extrusions. Okay, and then I finally got the 3-axis mill tuned up good with the Mach software running. I ran this same little program all day, which pretty much covers the entire base of the bed. So it covers your maximum X and Y, pretty much from the back end of the table to the front end of the table, which is that end, to the back end here where the motor's mounted. And I wound up tuning the stepper drives are actually very capable. So, well, first of all, what makes this very capable is having the smooth stepper control board. This control board does output 0 to 10 VDC to control a spindle. And then I've got two wires I haven't made up yet. They go to pin 14 and negative on the 24-volt power supply here to provide, which I have ran over here to two terminals, to provide limit switches on the system. So, and also this board is capable of, I've got 3 driver axes on here right now. So we have, well, the way I actually have mine set up right now is we have your X and your Z. X, and this is your Z drive, that's X, and this is Y over here. That's just the way I have them wired down here on the board, on the control board. This is kind of a generic smooth stepper board I bought out of China, right along with the 3 drive boards. So I started out conservative like everybody else. I started out on 400 pulses on the first setup. So I went conservative 400, and because I'm using the 16 millimeter 5 millimeter per revolution, so you move 5 millimeters linear every time this goes around one rotation. And so to convert that to inches, we're looking at dividing into 25.4 revolutions. So it takes 5.08 revolutions per linear inch with this ball screw. If you're using metric and you're running SAE units, or you're running inch units using metric ball screws, it's just fine. So I started out on the drive, on the amperage, I started out pretty high. Like, I think I started out at 3.76 peak and 2.69 on the current, and then I backed off because the motors were warm to 3.32. Now I've backed all the way off to peak 1.92, which basically switch 1 and 2. 1 is on, 2 is off, 3 is on, and that's exactly where we're at. So 1's on, 2's off, 3's on. So let's see, we're on pretty low amp setting. Let me focus back in for you. Yeah, so we are actually on 1.92 peak, a little under 2 amps, and 1.36 RMS on the drivers. And on the, this is what's amazed me, is that I started out in 400, went to 800, and every time I micro-stepped up, I could run faster on my rapid traverse, and I had smoother, more accurate movements. So now I'm actually running at, let's see if I can zoom in on this for you. So on the pulses per revolution, I'm actually running the 12,800 pulses per revolution. And then we multiply that times 5.08. And basically what you get is, some of you have already done this in your head, more power to you. So what did I say? Yeah, it takes 5.08 revolutions for 1 inch, for 1 linear inch. And we're going to do 12,800 pulses, so we're going to times that, or multiply that times 12,800. That is 65,024 pulses per revolution. Now that sounds like, oh, that's way too much. It's not. And this little low resource laptop has no trouble. All it's doing really, this laptop is sending the command lines, you know, several lines ahead to the stepper control board. And then the stepper control board actually takes care of the clean pulse trains, and it's 100K, so you can do 100,000 pulses per axis per second. So that's really still way above what we have here. So we're going to let's just go in there and I'll show you so you can see for yourself in motor tuning. We're going to cruise on into motor tuning. And if you look down here, I actually have, this is what seems to work best. I basically set it to 65 inches per minute. I could run 70, 75, but I noticed I was missing steps when I ran a long CNC profile program on some letters. So I backed off to 65, that's 64.98 inches per minute. And you can see that we're pulsing 65,024 pulses per revolution per unit. So that is pretty good. And then I've got my velocity at 20. That seems to work really well. I noticed too, if you set the velocity too maxed out, like if it takes longer to ramp up, the stepper motors on the open loop control system like this have a tendency to miss steps. So 20 worked out really well. I actually ran the same program all day, and I have all three axes basically set the same way. The Y is the same. The Z I have a little different because the Z's, I need to work on it a little bit. It's a little tighter axis, and so, and it doesn't have to travel as far or even as fast, really. I mean, Z only has about 4 inches of total travel, so I've got it set at a maximum of 40 inches a minute with 22 acceleration. So inches per second on acceleration. And that all is really, really smooth. And the motors, once I got to this point, the motors ran cooler, like they're just lukewarm to the touch, even after they've been running or setting like they are right now for a while. So I'm just going to cancel out of this, but just wanted you to see the motor tuning. So now let's run this program. So I'm going to go to the tool path so you can get a better view of what I'm just cutting some letters out that I grabbed out of. Actually, I use this software called called Outline Art, and you can type letters and save them as DXF files, so they work really well. That's how I did the letters. And the CAD drawing for the machine I did, MCO Construction uses Autodesk Inventor and AutoCAD Mechanical, so that's how I drew that up here at work. So let's just run this thing. So right here, if you go over to just Regen Toolpath, which has already been regen, it just puts everything in the open, and then basically what will happen is when I run the code, we're going to hit cycle start, and I'm going to back off so you can see the machine start to move, and then I'll walk around the front and we'll watch it. So I just hit cycle start. You can see the Z went up maybe, and the X is moving across there. And we'll look a little closer on the toolpath. The Z Z is about to drop down here in a second. And there the Z drops. We'll look at the tool path. And we're cutting the C out right now. Let me walk around to the front of the little machine. So pretty much this is about 23.9 inches of travel on the Y-axis, which is this long axis, and on the X we have 15.5, and on the Z we have 4.5 inches. It's more than plenty. I'm going to hold still so you can actually see the machine move. It's kind of noisy in the shop, so I don't know if you can hear the motors. I mean, between the compressor back here running, and I've got a couple fans in the background going because it's about 100 degrees outside every day, which makes the inside of the shop about 120 degrees, it seems like. But anyway, this is, I think I'm cutting it at 48 inches a minute, and we can see that if I switch over to the program run screen. So if I go over here, we can actually see our inches per minute right here. So I set it for 48, so we're running 47 to 48 inches a minute. And then there's your tool path. So it's cutting that large C out right now. Then I scaled the letters down and basically made them, run across the entire distance of the whole CNC mill table, so that it'd give it a good workout. And I ran this program probably a dozen times while I was working on other parts today. So tomorrow I plan on having we'll just stand still for a minute so we can see it actually move, because 48 inches a minute and then 65 inches rapid traverse is not all that fast, but it's fast enough for this size mill. And I think you'll find out tomorrow when we actually cut some parts out just how well these C7 metric ball screws really perform, and the slides are decent. For the price, this is probably the most inexpensive table you can build on a 3-axis system and still get really good performance and repeatability. Kind of hear the motors over the loud noise in the shop. I didn't do anything fancy on this. This is just some, you guys all know what this is, everybody does. It's just some wire cover, almost like what they use in automotive. But it works really well without having to buy the Aegis cable carrier stuff. Now the cable is Aegis continuous flex cable. So the way I've got this cable's flexible, moves with the X-axis, and doesn't interfere or move the connections in any way. And yeah, I did just use terminal blocks to connect. I like those connectors better than the plugs. I had some little plastic plugs on there and they didn't seem like they made good connections, so I took them off and put the terminal blocks on, and all you have to do is make the same colors up with the motor is there, color coded on the Aegis cable. But anyway, that's probably enough video on that. We can watch it. It'll be a lot cooler to watch it cut the actual letters out tomorrow. I'm going to put that board right there on. That'll be my spoiler board. And I'll put a cross brace across the middle right here to support the center. And we'll latch that down. This is where it's at in the tool path right now if you look at it. So it's moved quite a ways across the table. It's cutting on the end right now. And it's cutting that at a rate of, it's programmed for 48 inches a minute. So if you look over here, I don't know if you can see the code. There's a 48 up there. Just went by. There's another one. Right there. F48. So that's what it's programmed for. It seems to average 7, and you can hear the motors accelerating and decelerating as it ramps and goes around the arc. Really, those aren't even arcs. That's just a lot of little lines connected together to make it look like an arc. So it's arc interpolation, really. 3-point arc has come out a lot smoother. Anyway, probably long enough. I'll go ahead and upload this video, and we'll pick it up from there tomorrow. Stay tuned.